All right, folks. How's it going? You guys ready for your last day of calculus lectures for 2024? You did it. Before I dive into the new stuff, does anybody have questions on what we did yesterday or last time with optimization? I don't know if we got to looked at any of the homeworks yet or had any questions about anything yet. Okie doke. So today we're going to do two topics. The first one is something called Newton's method. And the idea here with Newton's method is we're going to make a series of linear approximations to estimate the value for a function. So for example, if our function is this blue curve f of x, and we want to approximate the value at, say, when x is equal to 4, I'm sorry, at x, this point r at x4. So what we'll do is we'll create a linear approximation, figure out where that intersects the x-axis, use that new value as an input, build another linear approximation, figure out where that intersects the x-axis, use that as a new input to make another linear approximation, find out where that crosses the x-axis. And that's kind of the idea. Okay, so it's just a way to approximate the value for a function by using a sequence of linear approximations. So to find that next x value, or that next value in our sequence, we take the previous value and we subtract f of that value divided by f prime of that value. So far, so good. And if we did this infinitely many times, like if I went and split the distance from like x1 to x4 into infinitely many slices, I'd get the exact value of f of x, right? So Newton's method, not a like the initial conditions matter, right? Like it's not like a perfect approximator because weird things can happen. So like if we look at an example like this where we have lots of extrema kind of localized in one area. So if this was my x1, I approximate. So here's my intersection. That's my new input for my next approximation. I do it again. Look what's happening. It's going to be like zigzagging all over the place and maybe not settling down to a specific value. So that initial condition matters a little bit, or can matter a lot a bit. Let's run through an example here. Now, the way I like to do this is I would set this up on my calculator as like a recursive thing where I'm just going to like do some second and enters and go from there. So my f of x here, so it says starting with x1 is equal to 2. Find the third approximation, that's x3, to the root of the equation x cubed minus 2x minus 5 is equal to 0. So there's my function. And then I'm going to need my derivative. So there's that. So far, so good. So I'm going to set this up on my calculator. So into the y equals, I'm just going to type my function, my f of x. And then my derivative, my f prime of x. And then I'm going to set my starting value. So that tells me it's 2. So I'm just going to press 2 and then enter. And then I'm going to fill in this formula. So my x sub n is 2. So I'm going to have like ants minus, and then I'll do vars, y vars, function y1 of ants divided by vars, y vars, function y2. That's my derivative of ants. Press enter. So that's my x2 then. If I just press enter again, that's then my x3. So this is my third approximation to the solution to the equation x cubed minus 2x minus 5 equal to 0. So just to kind of compare that, if we look at the graph here, it's probably fine. So x equals 2 is up here somewhere, right? I'm sorry, this is 2. Yeah. So we're just kind of sketching in from there. That's not a very good picture. Let's do that. So here's x equals 2. So it's kind of drawing in my approximation. If I look at the exact value there, so if I want to find out what that actual 0 is, pretty good, right? Now, did it help that we start with a value that was already really close? Yeah, but it'll do. So it says use Newton's method, and our next example says use Newton's method to find the 6th root of 2, correct to 8 decimal places. Okay, so I want to start by rewriting this as like a polynomial equation. What polynomial equation is going to have the solution, the 6th root of 2? How about x to the 6th is equal to 2, right? Or x to the 6th minus 2 is equal to 0. That's what I want. So that's my f of x. And my f prime of x would be 6x to the 5th. Okay, now I need to decide on a starting value. So what number do I know is going to be less than the 6th root of 2? Well, closer than that, though. How about 1, right? Because the 6th root of 1 is just 1, right? The 6th root of 2 is to be closer than 0. I'm afraid with 0, I'm going to end up with a 0 denominator. So 0 is probably a bad one to use. And it says we want this correct to 8 decimal places. So let's just go ahead and write the 6th root of 2 down for a moment to make sure that I have the 8 decimal places there that I desire. It's 4 decimal places. 6, 2, 0, 4, 8. Okay. Oh, go away. You stupid thing. I just want to... Oh my God. I just want to use my controls. I hate you. I don't even want you to show up. I don't know why you have to. All right. So I'm going to go to my y equals, and I'm going to replace that stuff with my function and its derivative. So I'll start by preloading. I'm going to have ants minus y1 of ants divided by y2 of ants so here I have 2 digits correct, right? I have 1.1. So I'll hit enter again. Now it looks like I have 3 digits, 1.12. And I do it again. So now I have 3 digits correct. I have 5 digits correct, right? I'm all the way out to 4. You guys see what I'm looking at? So I do it again. And I'm out to, all the way, I got 6 decimal places correct. I'm all the way out to here. If I do it again, got it. So if this is x1, it's x2, 3, 4, 5, 6. So it took me 6 goes to get an approximation within 8 decimal places. That's not too bad. Is everybody okay with what I'm doing on the calculator here? Okay. Find correct to 6 decimal places the root of the equation. Cosine x is equal to x. Since I want a root, the first thing I'm going to do is get it equal to 0. So there's my f of x. And then my derivative would be negative sine x minus 1. And I guess I need to find I need to find out what that actual value is, right? Because it says correct to 6 decimal places, which they just told me in the problem. It's probably fine. Oops. So there's, I gotta check my mode though. Yeah, I thought as much. That looked a little too linear for me. There we go. So there's my solution. Let's actually find that here. Just FYI, could I have solved this equation, cosine x is equal to x, without my calculator? I could not. I have no idea what I would do to try to do that. That feels hopeless to me. So my solution, oops. So that's 6 decimal places there. That's all I'm going to write down. All right. So what value do you suppose we want to use to start this guy out with? Just going to use 1. It's pretty close. If I look at the picture, everything is pretty well behaved in there, so I'm going to feel okay. I don't want to grab a part that's like too steep necessarily. If I have a calculator, I can always look at it. That's what we saw going on back here, where like things were not going to work out real well for us, as you're just grabbing the steep parts of the graph. We don't want that. All right, so I'm going to do 1, and then check this out. I don't need to recopy all that stuff. It's the same formula every single time. So let's see. So I got 1 decimal place. I got 3 decimal places. There's 6 decimal places. It took x4 to get to all 6 of them. You guys feel okay? It's basically all you're doing in this section is just using your calculator to do this Newton's method. Well, it's x1 is 1, right? So then I did 3 Newton's method, so I ended x4. But does that feel okay? Pretty straightforward. All right. So our last section we're going to be talking about are antiderivatives. So the question here is, if I have a derivative, can I recover the function that I differentiated to get the derivative? So it's going backwards, what we're trying to do here. So we say a function f is called the antiderivative of f on an interval I if f prime of x is equal to f of x for all x in I. Right? So if I have a function I differentiate, I get the derivative, must have been the antiderivative. Observation. Let's say f of x, all right, so let's say our derivative is 2x. What could have our original function been? X squared, right? But what if we had x squared plus 1? What's that derivative? 2x. Or what if I had x squared plus 2? What's that derivative? What are you noticing here? How many antiderivatives can I have? Infinitely many, right? In general, we would say that f of x is x squared plus c, where c is some arbitrary constant, right? So like, here's our example of, there's my f of x, my g of x, and my h of x from, feels okay? Okay. So if f is an antiderivative of f on the interval I, then the most general antiderivative of f on I is f of x plus c, where c is just an arbitrary constant, what we observed from above. So let's practice here, finding the most general antiderivative for each of the following. So what's going to be the antiderivative of sine x? What can I differentiate to get sine? Close. Negative cosine. Very good. Why has it got to be negative? Perfect. Exactly right. Okay. What about 1 over x? Very good. And then again, if we want the most general, we got to put a plus c at the end. How about x to the n? So let's just do a couple of examples. If it's x to the first, what would have we had to differentiate to get that? Would have had to have an x squared in it, right? But when I take the derivative of x squared, what do I get? 2x. How do I get rid of that 2? Divide by 2. Right? What if I had x squared? Well, its antiderivative has to have a x cubed in it, right? But when I take the derivative of x cubed, what do I get? 3x squared. How do I get rid of the 3 out front? Divide by 3. Anybody picking up the pattern yet? Okay, what is it? Well, it's n plus 1 over n plus 1, right? That's good. Does that feel okay? How we got there? Why do we have can't equal -1? Well, it's because x to the -1 is the antiderivative is natural log, right? Everybody feel decent there? Okay. So what we want to point out to you is some general rules for anti-differentiation. So if I have a constant times a function, I can pull the constant out and just take the antiderivative of the function, just like we could for differentiation, right? If I have the sum of two functions, I can just take the antiderivative of each of them separately, just like we could for derivatives. We have our general rule for any power function that we just identified before. There's that one. What's the antiderivative of e to the x? E to the x, because the derivative of e to the x is just e to the x. Antiderivative of cosine is sine. Antiderivative of sine is negative cosine, as we observed. Antiderivative of secant squared is tangent. Antiderivative of secant times tangent is secant. What are you noticing here? This is like the derivative going this direction, and this is like the antiderivative is just the reverse, right? So guess what? If you know the derivative definitions, the derivative shortcuts, do you know the antiderivative shortcuts? Yeah, you do. You just go in the opposite direction. Yes, Mr. Kulak, I am real happy whenever the time I spent memorizing something comes back and it's useful for something else later on, right? It's like that was time well spent. You know, this thing you should recognize is the derivative sine inverse. This one we should recognize the derivative, or the derivative tangent inverse. And these guys, we didn't do any hyperbolics. You don't have to worry about those. It's not a part of the AB calculus course. So here it says, find all functions g such that the derivative of g is 4 times sine x plus 2x to the 5th minus squared x all over x. So let's do this as two separate chunks, right? And let's just do that. I know that I can just ignore the 4, right? So what's the antiderivative for sine x? Negative cosine x. Now this piece, I'm not going to do it like that. I'm going to simplify that a little bit. Do some algebra to make my life easier. What algebra am I going to do? I'm going to break it up and write it as two fractions with a common denominator. So that becomes 2x to the 4th minus x to the negative 1/2. So what's the antiderivative of 2x to the fourth? Well, I'm going to ignore the 2, right? And then I'm going to say x to the 4 plus 1 over 4 plus 1. Does that feel good there? And I'll have minus, and I'll do the same thing here. I'll have x to the negative 1/2 plus 1 over negative 1/2 plus 1. Everybody's okay? So if I simplify, and then I need, it says all functions, so I need a plus c at the end. So if I simplify this down a little bit, I have negative 4 cosine x plus 2x to the 5th over 5 minus x to the 1/2 over 1/2, or really just negative 4 cosine x plus 2x to the 5th over 5 minus 2 square root x. Feel okay? Very, like, if you felt good about the differentiation process, this should be okay right now, right? Pretty straightforward. Okay, so let's do just some more examples. It says find f if f prime of x is e to the x plus 20 times x plus, or 1 plus x squared to the negative 1, and f of 0 is equal to negative 2. Why are they giving me this? I'm going to use that to solve for c. So I'll be able to find the actual specific f in this case, because I know a point on f. So whenever you're given a value from the original function and asked to find the antiderivative, the reason you're getting that value from the original function is so that you can find the specific value for c. All right, let's start doing antiderivatives. So e to the x, what's the antiderivative of that? E to the x, piece of cake. What in God's name am I going to do with that? Everybody's cool? Do we recognize this thing? Tangent inverse. You see it now? If you say so, Mr. Kulik. So I just ignored the 20. Okay, and then it says f of 0 is equal to 2, or negative 2. So I have negative 2 equals e to the 0 plus 20 times tangent inverse 0 plus c. E to the 0 is 1. Tangent inverse of 0 is 0. So c has to be negative 3. So my final answer then is e to the x plus 20 tangent inverse x minus 3. Feel okay? You're like, where's this been? This is so much simpler than what we've been doing. Well, it's because we're entering a new, like, this is the bridge to second semester. So we're going to be building off this idea all second semester. So this is like day one of derivatives where you're like, this isn't that hard. And then eventually it gets hard because we build up a bunch of complication around it. But this is the very beginning, so. It says find f if f double prime of x is equal to yada, yada, yada. And then f of 0 is 4, and f of 1 is 1. So notice here that this time we got 2 of these guys. Why are we getting 2? since we're going from the second derivative back to f, we're going to have two c's that we're going to have to find. That's why we're going to need 2 points on f. Let's start though. So we'll start with f prime. So again, I'm going to go term by term. So I'm going to ignore the 12. What's the antiderivative of x squared? Okay, let's just do that way though, right? Is that okay with everybody? Okay, and the antiderivative of x is over, very good. And the antiderivative of 4 is 4x. And then we need a plus c at the end. Let's clean this thing up a little bit though. Now I'm going to call this guy actually C1 since I know I'm going to have 2 constants. So far so good? Okay. So now to find f, I'm going to be using this. So f of x, I'm going to ignore the 4. What's the antiderivative of x cubed? Excellent. And the antiderivative of, again, I'll ignore the 3. What's the antiderivative of x squared? Good. And the antiderivative of x? And the antiderivative of c1? c1 at times x, and then we'll have a plus c2. So far, so good. We'll do a little cleanup here. So we're going to have just x to the 4th plus x cubed minus 2x squared plus c1x plus c2. Now, how many variables do I have in this equation? Or unknowns, I guess I should say. Really just 2, right? The 2 coefficients that we're missing, C1 and C2. So what I'm going to do is create a system of 2 equations. I probably won't actually need it because this is going to be super helpful. So f of 0 is going to be 0 to the 4th. Well, I should say 4. Let's do that. Squeak it in there. And then plus 0 cubed minus 2 times 0 squared plus c1 times 0 plus c2. What's that going to tell me then? C2 is equal to 4. So I can then use that. So I know 1 is equal to f of 1, which is going to be 1 to the 4th plus 1 cubed minus 2 times 1 squared plus c1 times 1 plus 4. Everybody feel okay there? So what do I get here? I subtract 1 from both sides. Those guys go away. I combine my like terms here. That's a negative 1. And I add it back over. Right? And then I subtract. So my f of x should be then x to the 4th plus x cubed minus 2x squared minus 3x plus 4. And again, you could check that on your calculator. If you type that in, you can check to make sure that these are actually points on it. Right? If I plug 0 into this, I better get 4, and if I plug 1 in, I better get 1. In addition, I could take the derivative of this twice and make sure I end up with this thing as a checker. Does that feel okay, though? A little bit more to do there, but still no big deal. The graph of the function f is given in figure 3. No, I didn't apparently copy that in. Let's grab that then. Find the graph of its antiderivative. Let's input that real quick. All right. So I'm looking at the derivative here, correct? So if I look at this piece, that tells me the function is decreasing. How can I tell that? Because that derivative is negative there. So under the x-axis. Everybody agree? And if I look at this piece, that tells me the function should be increasing. So what's happening at 1 then? It's a local minimum, right? If we're going from decreasing to increasing. And then I can see that from this section, we're decreasing again. So what happens at 3? Equal max. Now let's think about the second derivative for a moment, right? The second derivative is going to be 0 where the first derivative has its extrema. So my inflection point should be at 2 and 4. The first derivative is increasing, so my second derivative then is going to be concave up on that section. From 2 to 4, my first derivative is decreasing, so my function should be concave down. And then here we're increasing, so we're back to concave up. Is everybody okay with how I came up with that information from looking at the picture? I'm going to grab this picture again and just draw it on a clean one. So I know I'm going to have a local minimum at -1. So let's just pick a spot for it. And a local maximum at 3. So I'm just going to pick a spot for it. Do the y coordinates matter at all? Not a bit. So going to 1, we need to be concave up and decreasing. And then we're going to change here, still being concave up to 2, but we need to change to increasing. At 2, we're going to switch concavity. Let's try to do a little bit better than that. Right? And then there's our local max. So then we switch to decreasing, but we're still concave down until I get to 4. And I change to concave up again. Does that feel okay, everybody? And how I kind of drew that? Okay. Next example says a particle moves in a straight line and has acceleration given by a of t equals 6t plus 4. Its initial velocity, v of 0, is -6 centimeters per second, and its initial displacement, s of 0, is 9 centimeters. Find its position function, s of t. What do I have to remember about the relationship between acceleration, velocity, and position? Yeah, they're all derivatives of one of each other, right? Velocity is the derivative of position. Acceleration is the derivative of velocity. So we want to find the antiderivatives up, right? So if I'm looking at acceleration to start with, the antiderivative of t is just going to be, and the antiderivative of 4 is just going to be 4t. We have a plus c on the end. Now if I know that v of 0 is -6, That tells me that the c is just -6. So my v of t, if I clean things up, is 3t squared plus 4t minus 6. And now to get the position function, that's the antiderivative of velocity. So we'll kind of do the same thing. And here I know that 9, if I plug 0 in. So that's just telling me that c is 9. So if I clean this up, there's my position function. That feel good there? Okay. Last example, a ball is thrown upward with a speed of 48 feet per second from the edge of a cliff, 432 feet above the ground. Find its height above the ground t seconds later. When does it reach its maximum height? And when does it hit the ground? So what is this telling us? And what is this? Okay. So so I need to start with what function? Acceleration, right? Am I given the acceleration function? I'm not. Do I need it? I do not. Why not? Just gravity, man, right? It's the acceleration due to gravity. What is it, though? Who remembers? Acceleration due to gravity. 9.8 meters per second squared, right? What's the problem with that, though? What unit are we in? Feet. Does anybody remember gravity in terms of feet? It's 32. But I've made a mistake here. What's my mistake? Negative. Yes, thank you. Good catch. So that's my start. What's the antiderivative of -32? Well, let's use t, and we got a plus c there. But what's c got to be? 48. Everybody's caught on here that if I have 0, if it's like f of 0, then the c is just whatever f of 0 is. Okay. So what's the antiderivative of that? And what's c got to be? 432. Okay. So that's my position function. What else does it ask? When does it reach its maximum height? How do I find that? So I'm going to take my first derivative, which is velocity, and set it equal to 0. Right, I'm just going to do a first derivative test. So negative 32t plus 48 equal to 0. So t is going to be 48 over 32, or 3 over 2. Now, common sense will tell me that if I'm standing at the cliff, I throw it up, there's only going to be a maximum, one maximum. It's clearly got to be the, right there early on. Everybody's okay with that I don't actually need to check that. You could if you wanted to. And if it were a more complicated situation, you might want to. Okay, when does the ball hit the ground? What are we looking for here? It's when S of t is 0, right? Oops. T. Okay, so let's divide the whole thing by negative 16. Get the leading coefficient to be 1, particularly since I noticed that 48 is divisible by 16. And 432, it is 27. Good call. I notice that's factorable. Yes. Right? No, it's not. I lied. It's not factorable. We got a quadratic formula, that guy. All right, let's see. We have 3 plus or minus. 9 plus 108 is 117 over 2. And I guess that's divisible by 3, right? That's going to be 9 times 13, I think. But remember, this is time, right? So which one can I throw out immediately because it's time? This one. Why? Yeah, this is less than 0. So there's my answer. Whatever that comes out to. The textbook says it's about 6.9 seconds. In case you just really needed to know how long it took that ball to hit the ground. What did we elect to ignore? Wind resistance, friction, basically, right? And I guess elevation. Gravity varies by elevation, but like, here, we're not talking about all the elevation in the world here, so it's probably fine. We'll assume we just started 320 or 432 feet above sea level, and at that point, it's like, gravity is basically the same. If we're on Mount Everest, maybe it's different. Or if we were in an airplane throwing the ball out the window to a different airplane, there you might have some difference in gravities. But that's it. That's the gist of these 2 sections. Hopefully this felt reasonably straightforward. So as a reminder to you, the 3 things that we've done this week, the 3 sections we've done this week can appear on your midterm. I would expect to see an optimization problem on the midterm. I'd expect to see an anti-derivatives problem on the midterm.
The derivative section?
It could be a multiple choice question. It could be it could be an applications question if it's like built around acceleration, velocity, position. Like that's a perfectly reasonable multiple or applications problem since it's real world applied. Feel okay? Okay. So your last problem set for the year It's going to be the homeworks from 4.7, 4.8, and 4.9. You know, try to have those kind of wrapped up middle of next week or so. We'll see you guys 2 times next week. We'll talk more in detail about like review stuff for the exam, like what I would do. We'll see if I can get you something together in some form, whether it's like a PowerPoint we go through together in class or something else. But that's the gist of it for the semester.
Well, like practice-wise, what do you recognize?
So when we talked about the midterm, so we talked about there's like some different sections. So first things that I would probably go through is I would go look at what's the stuff that I have to have cold memorized, that like I need to have this stuff to be able to do, right? So like I need to have my derivative rules. I need to have my big value theorems, like, you know, intermediate value theorem, extreme value theorem, mean value theorem. Got to have those, got to know exactly what they say and when to use them and how to use them. You know, I got to know like my basic facts, like that differentiability implies continuity, but the reverse is not true. So I'd want to do that. And then I would look at, you know, to review for the MCQ stuff, I'd look at the MCQs that I've assigned so far. You know, for the limit problems, there's really like the stuff we did in chapter 2 and then the L'Hopital stuff. So I'd probably just pull some problems from chapter 2 and L'Hopital and practice, make sure I can do that kind of thing. And then I can recognize when to do one or the other. The good part about this is that L'Hopital is kind of like a skeleton key, where like all those problems that you had to do like really crappy algebra stuff for in chapter 2, you can now just L'Hopital it. And most of the time that's going to be fine. You might have to remember that like some of these L'Hopital problems, you have to do some algebra in between to see if you can cancel anything before L'Hopitaling again. But you know, for the derivatives practice, I'd go back to test 2 and 3 where we did most of our derivatives. Make sure I can do those things. Can I use like the chain, quotient, and product rules in combination? You know, it won't be crazy combinations. You know, and it's not like I'm going to have like a problem where you have 2 product rules and 3 chain rules that are all nested together or something like that's not going to happen. But you should be expected to be able to do something like, you know, take the derivative tan inverse of x squared plus 7x. Should be able to do something like that, right? That's just a chain rule. Should be able to do something like, you know, find the derivative of natural log of x over x squared. Just a quotient rule, right? Should be able to do stuff like that where you have 1 or maybe 2 derivative rules in combination with the shortcuts. You know, like the definition and theorem questions, like I would definitely want to know how to show like a piecewise function is continuous. So you need to probably use your definitions of continuity to talk about the parts, and then you have to check the intersection, like the joining of the 2 pieces to make sure they join up the right way. I'd want to know piecewise functions are differentiable, how to show that. Those kind of all landed in the same test or tests. You know, I'd want to be able to use the mean value theorem to find a place where the derivative, or find if the derivative could equal the average rate of change over a closed interval, and what that average, what those values of x would be if it does exist. So that's like using the mean value theorem. I'd want to be able to show that like, you know, a function f of x can take on a certain value. That's like using the intermediate value theorem, right? So these are all kinds of problems that we've done before. I'd probably go through my old tests and kind of like identify whether this is like, okay, some of these problems, is this like a definition problem or theorem problem? Is this an application problem? Is it, you know, like just a straight derivative or limit problem, and probably start pooling that stuff together. and kind of decide which sections I'm strong or weak in and spend a little bit more time, in those weak sections. As far as the application stuff goes, let's think about that. Like, what would we see in there? So we have, I'll tell you, you'll see optimization. I already told you that. What's another big application problem that we've done? Related rates. You should expect to see one of those. What else? So you could be antiderivative, especially related to velocity, position, acceleration. Max and min. Yep. Concave up, concave down, inflection point, like all that stuff, I think is all fair game as application problems. That probably about sums it up. It's always stuff like that, which again shouldn't be too bad, right? Those are all, you don't have to do all of them. Remember, again, like the application problems are 4 points per, so you really just need to be able to do 2.5 of them. Yeah, Hattie.
Sections have only 10 points.
No. They all have much more than 10 points. They're all going to have, like, what do I say up here? Like 10 to 20. I guess it should be really more like 15. But they all have, there's no section where you have to do every problem. Every section you have enough choice to avoid, one or two of them at least. And, if you know what to do, if you're just hunting for partial credits, maybe you have to try to do all, at least make some progress on all of them. But
It's not a bad idea.
Again, like I would only do that in the sections where I feel weak, right? Like the sections I feel strong, I don't want to burn a bunch of time getting like 18 out of the 20 points in a section because they don't carry forward. That's 10, whether you scored 18 of them or you got 10 of them. You know what I mean? But that's probably the way I would go about studying this, is I would start with the stuff that, like, collect the stuff I know I need to have memorized and, like, have a list. And as I'm doing other reviewing, I'm like, oh, yeah, this thing should go on my list. Let me put that on there. But it's open calculator. Keep that in mind. That helps a lot, right? And then I would just, I'd start on the areas where I feel the weakest. If I feel weakest in application, and be like, okay, I got a pretty good idea of what kind of application problems I need to do. Let me go through and run through some more related rate stuff. Let me run through make sure I do the optimization homework. Let me make sure I've done, these like max, min, inflection point, concave up, concave down, increasing, decreasing kind of problems. Let me make sure I can do that kind of stuff. So at least there's some of that stuff in there that I feel really good about, so I can choose that and be like, okay, I can get 4 on at least that kind of question if it comes up, because they're all kind of the same. It'll be fine. I have my calculator, like the plugging in of numbers and the solving, that should go quick now because I have a calculator. I don't have to mental math it. You know what I mean? Does that help? Is that kind of what you're looking for? Yeah, of course. Like definition and theorem stuff, like you should know when things are differentiable or not. Like you should be able to look at a function and know where it's differentiable or not. The graph specifically, like if I give you the graph of some function, you should be able to look at f and tell me where f prime is differentiable or not. What are the 3 things you should be checking for? Corners, and the third one is vertical asymptotes, vertical tangents. So like cube root function is the classic, where it has that vertical tangent. That, like should know stuff, like those are the big ideas. It's not going to be like exceptionally granular. I tried to pick, questions and concepts that were like the big ideas that you like, if nothing else, you should know, like recognize these terms and recognize these ideas, because these were the big ideas, differentiability, continuity, how to do a limit, how to do a derivative, what are the big theorems? Can you use those in context? The big definitions, can you use those in context? Is that kind of what you're looking for? Yeah, Addie.
So the theorems are the only big ones we did for IBT.
The value, the three intermediate value, mean value, and extreme value.
And then for the definitions, we don't need to give a title to them.
Yeah, the big one is going to be continuity and differentiability. Those are the big two definitions that you gotta know, and you gotta know how to show those things, right? So if I just give you some function, particularly piecewise, those are usually the ones where it's hard, because most functions we just know about the continuity of them, because from algebra 2 and pre-calculus. The piecewise ones are sometimes tough because it's hard to usually picture it in your head what it's going to look like. Does that feel okay? So yeah, that's kind of where I would start. And again, I'd probably start early, right? Like I'd rather do, 30 minutes a day for a week, for 10 days than one day of 6 hours, right? Like, not that one day of 6 hours is bad, but I think it's usually a little bit more effective if we can parcel it out and give your subconscious some time to absorb this stuff as you're reviewing it. I am someone that sometimes it takes a little bit of time for stuff to just sink in. But the hope is that when you go back and start reviewing this stuff, that it's oh, this stuff felt so hard back in September, and I'm doing this now, and it's this is why would I think this is hard? This is pretty straightforward. And that's just because you hadn't caught up, by the time test time rolled around back in September. But that's not uncommon. Yeah, Jennifer. Sure. So again, keep in mind that you'll not be able to finish every question on the exam. Time is such that it's probably impossible, but you don't need to, right? You need to get 10 points in each section. How much things are worth is clearly labeled. If you feel real good, I would just do my 10 points worth to start. Make sure I have time to do the stuff, struggle through something that don't feel good about, rather than spending a bunch of time doing stuff I do feel good about. Doing extra stuff you feel good about is kind of don't do that. At least not initially. If you have time at the end and you don't want to keep grinding away and oh, let's do an extra one here or there in case I boo-booed something, that's totally fine. But I wouldn't do that until I've had a chance to okay, I've done 10 points worth of questions in all 5 sections. Now I'll go back and start looking for, the sections I felt bad about and do some extras in there. But to look at this, you need to do, at the minimum, you need to do 5 MCQs, 5 limits, 4 derivatives, 3 definition theorem questions, 3 application questions. The good news is everything on here is single part. It's not you have to do these 10 things. It's not part A, B, C, D for anything. The related rates problem is just going to be here's the situation, find the rate of, the rate of change of height with respect to time or something. Just one thing. That's all you need. It's not going to ask a bunch of different things, or it's going to be here's your function, or here's your derivative. Find the, local min and max for this. It's fine. It's one thing. Do I got to do a bunch of stuff to do that? Sure, but it's just that's it. One thing to do. So again, you say oh, I got to do 3 definition questions, but it's not really, it's just one part. like show this thing as continuous. Okay, like it's one thing to do. It's not like show it's continuous and then show it's differentiable and then show it's this and then do this and then tell me what this, like there's none of that. Yeah.
Can we get our test scores back next week?
Yeah, I can give them to you right now, I think. Ooh, no, I can't. Selena, that's right. She was supposed to finish hers. Yeah. So, like if you want to look at it, to look over, see how you did before, I'm happy to do that after class and let you take a look at your parts. If you're trying to there's test 4 is the one I really need to work on, totally fine. Happy to let you look at it. But the hope is to give those back to you guys next class. Even if Selena hasn't taken, I think at that point we just need to hand it back. It's like, Selena, go to the study hall and finish this thing. I'm giving these back, kind of thing. For those of you guys that filled out the questionnaire saying that you need to do a retake, I got all your stuff. Everything is in the testing room study hall file for you whenever you're ready. So I printed it up, made your new version. Same formats, same curves, all that'll be the same. So study your old one, probably helpful. Be same ideas, same distribution of questions, same types of questions. Will they be different? Sure. But, you may see some repeats or some that are close enough to being repeats that it's like, okay, this is the same problem with different numbers in it, So it's a good place to study from. But yeah, in general, we're right there at the end. Sound okay? Of this list of sections, which ones sound the scariest? The application section sounds the scariest. I'm just trying to get an idea for you if I do some class review stuff, what section, what kind of topics or areas should we be looking to do a review? The most targeted review that'll help the most people is kind of where I'm just trying to get an idea. The application. Okay. Cool. All right. I don't know. I don't have anything else to say. It's been a fun semester, guys.
First time in semester.
Yeah. No, to be honest with you, it'll be better. Here's what
It's like my lifesaver in CT for helping me study.
Oh, you just mean for the test timing?
Last minute, yeah.
Okay, that's fair.
Because anytime I have a question, I really have to wait until CT and then ask Emily.
Well, you might have to, bribe Emily into studying with you the day before instead.
It's not like studying with me, it's more like tutoring.
Well, sometimes that's good for both parties, right? Sometimes.
Can I see my test?
Sure.
That was